A very good day to everyone. We are from Team 10. Today we are going to summarize what we have done in our report 3B. I am Bang Hui-ying. First, we have listed out the assumptions that we use to solve the problem 3B. These are at the top column, we have the PNID diagram and also the transfer function. First, for the problem 3B, we need to find the GP and GD value for the condition of the positive and negative 5% change of refine rate at the top column. So first find the GP value. So we use a step change in the refine rate R from the 9.5 to 9.975 kmol per minute by using the method 2. Use the KP formula, time formula, tau and delta formula to solve in order to get the GP value, which is the distillate composition over the refine rate. Besides, we also for the disturbance we have two disturbance. First one is the feed rate, and also the second one is the reboiler duty. We also use the same method, which is method 2, to solve the GD in order to get the GD value by using the same formula. Next is for the second condition at the top column, which is negative 5% change of refine rate. We also need to find the GP and GD in order for the further analysis. And so we also use the method 2 in order to find the KP value, tau value, delta value in order to get a GD and GP value. These are the table that we summarize what are the parameters value we get at the top column. So next we look at the bottom column. PNID diagram and plot diagram we have learned in the problem 3A. So for this problem 3B, we also use the open loop step change response to find the GD and GP value. We also have the two conditions. First is the positive 5% change. So at the positive 5% change, to find the GP value, we use the step change in the reboiler, because at the bottom column, so is the reboiler duty. So we use the graph of bottom composition versus time step. For the disturbance, we also have two. One is the feed rate, and another one is the refine rate. So we also use the graph given to find the GD. The second condition is a negative 5% change. We also use the same method to find the GP, GD. GD disturbance is the refine rate also and the feed rate. So these are the table to summarize what are the parameter value that we get at the bottom column. That's all for me. Thank you.
Assalamualaikum, my name is Nur Rashid. I will present about general and rough stability criterion. Rough stability can be used to determine how many roots will have positive real part. Hence, if the polynomial equation is the characteristic equation, this method can be used to determine the stability of the process. Based on our problem 3B, we want to find the range of Kc value by using rough stability. So this is calculations to get the range value of Kc for the top column. So the first thing is we have to find the parameters value. For this part, Bang Hui-ying is already explained it at the previous presentation. So I just proceed to characteristic equations. So this is the formula for the characteristic equations. 1 plus G naught L equal to 0. G naught L is same with Gp times with Gc times with Gv times with Gm. So if we already know the value of that parameters value, we just substitute into the equation. At the end, we can get like this. But you can see there is exponent here. So we have to change it by using 1/1 approximation. So at the end, we can get like this. After that, we substitute again into the equations. At the end, the equation become like this. After that, we do a rough array to get the value of Kc, to get the range value of Kc. So the first row, the value in this row is come from these equations. For the first row, we take first coefficients, and then we skip one element, and then we take the next coefficients. So this, and then for the second row, we do the same thing. We take the second coefficient, we skip one coefficient, and then we take the next coefficient, which is 0. For the row 3, is B1. B1 is equals to 7.375 minus 0.008. 21 kc times with this part, and then we minus with this part and divided by this back. At the end, after we have to simplify, and then we get B1 1 plus 0.0038633 kc. So we have to let B1 is greater than 0, and then we get 1 plus 0.0038633 kc is greater than 0. 67.375 minus 0.0821 kc is greater than 1. And we have to simplify, and then we get this value. Hence, we do like this. Kc is greater than negative 258.8460 and smaller than x 206.4555. Next is for bottom column. For bottom column, we just do the same method, the same way to get the to get the range, the kc range. So we just follow, and then we can get the kc range. So that's all for me. Thank you very much.
So Assalamualaikum and hi everyone. So I'm gonna explain about tuning method for loop 1 and loop 2. So for loop 1, we're gonna use Cohen-Coon method. First, by using this formula, we get the value of k, tau and theta, and then we proceed to find kc, tau 1 and tau d for each controller. So for the proportional controller P, we got the value of kc 4060.6457, and for proportional integral controller PI, we got the value of kc and tau 1. You can see the value, right? So after that, the third one, for the proportional integral derivative controller PID, we got the value of kc, tau 1 and tau d. So by using Simulink for P, we got the figure for the block diagram of P controller, and this is the graph for P controller. After that, we also get the block diagram for the PI controller, and this is the graph. We proceed to the PID. This is the block diagram, and this is the graph. So after that, for the loop 2, we use the same method for like the loop 1. So first we're gonna find the value of k, tau and theta, and for the proportional controller P, we got the value of kc, and by using Simulink, we got the block diagram of P controller. Same with proportional integral controller PI, we got the value of kc and tau 1, and this is the block diagram of PI controller. And the third one is proportional integral derivative controller PID, we got the value of kc, tau 1 and tau d, and this is the diagram for this is the figure for block diagram of PID controller. Okay, that's all. Thank you very much.
Assalamualaikum and very good evening everyone. I am Fatin Izzati from team 10. So today I would like to talk about online Ziegler-Nichols method for both loop 1 and loop 2. Okay, first for loop 1, we have simulate this method in the Simulink, and these are the results. So as we can see, the kc value for PID is much higher than than PI or P. Okay, so these are the graph for P, for PI and PID. Okay, we move to loop 2. We also simulate the same thing into the Simulink. Okay, so these are the value of kc. The kc value for PID are still higher than compared to the other two. Okay, so these are the graph for P, PI and PID. Okay, lastly, the conclusion. So in conclusion, to complete the learning issue, first we have to conduct the feedback controller analysis at top column and bottom column. Then the transfer function and block diagram were developed during this process. Okay, then we determine the GP and GD for condition 1 of plus minus 5% change of reflux rate for distillate compositions or bottom composition with time step by using method 2. Okay, then we identify the parameter value in the calculation. Okay, next we use rule stability criterion in loop 1 at the top column and loop 2 at the bottom column to identify the appropriate value of Kc. Lastly, we use both tuning method for which is Cohen-Coon and Ziegler-Nichols method for both loop and compare the result to choose the best feedback controller modes. From the comparison, we decided that for loop 1 and loop 2, it is best to use PID controller because the value of KC is higher than the other two. That's all from me. Thank you.